again. Oh, and brilliant, everyone's here. Okay, so I think this will actually be a shorter meeting than usual, um, but not too short, probably like 30 to 40 minutes. Uh, Thanks for attending, at a weird time. Basically, this morning, I and my mom flew to California, and now we are vacationing in California at my uncle's house.
Nice.
And so, yeah, I just got caught up in things. So it's actually 3 p.m. where I am, though, of course, I'm not adjusted or anything. Um, and I got up very early, so, I'm a little tired. But but I just want to do a little bit of this because it's very fun. Um, and yes, thank you. I'm glad I can see you, Dima, as well. And everyone else is, of course, welcome to turn on their cameras, but doesn't have to. But it's still, it's nice at least to have one person so I can look at something that isn't just the void while I'm talking. Um, so I really appreciate that, Dima. Um, okay, so where we left it off, I had written the implementation of Okay, what is going on here? I'm just curious. Something does not live long enough. Wait, so why did this work? Yeah, so right now I'm having a compiler error, but it's not preventing me from running my code. Cargo run. Oh, cargo run maybe doesn't do anything. Cargo test. Cargo test okay. Right, because this is like test code. Of course. So what I just realized is this is test code, which means it's actually not this that's the trick here. Uh, this is in a mod block that is marked config test, which means this is only even compiled when I do cargo test, or there are other ways I'm sure I could get it to do that, but it's not compiled when I do cargo run or cargo build. So this compile time error doesn't show up when I do those because it's just in this code. Like the compiler doesn't even look at this code when I do those things. But cargo test it does. Okay, so this was intentionally bad. So I will for a lifetime error discussed in meeting 9. Okay. Oh God. Okay. Uh, Whatever. Like at a certain point, I don't care. um. Okay. Right. So last time I wrote iter, or we worked through iter, and iter is simple. It's simple, but it's more complicated than into iter to actually write. But what does it do? It's an iterator. Um, and you can call next on it, and it doesn't modify the list that it was built from, and it just gives you the ability to look at, it just gives you references to the elements in that list. And how does it do that? Well, this kind of functional REST code is still a bit of an incantation to me, so I have to think about it. This implicitly returns whatever it evaluates to. So we're doing self.next, and that's our optional reference to something dot map, and then if there's no next, then we just do nothing and we return none, which is the right thing to do because that means we're done iterating, right? If there were if this was none, we're done iterating. And there are a couple of ways you could end up there. You could end up there by having created an iterator over an empty list, and then next starts out as null, or we could have iterated all the way through, or starts out as none, or we could have iterated all the way through something that had stuff in it. But okay, so if it's none, this map gives us none. That's good. If it wasn't none, then we call it with this node, which is a reference to, initially the first element in the list, or initially the first node in the list. And what we do first is we update self.next to be the node after the current self.next. This is like, this line is semantically kind of similar to I++, or, it's closer to like cur equals cur pointer to next, right? This is self.next is equal to the node which was inside self.next's next. So this is like self.next.next in a sense. Or this is like self.next.next. It's just we can't do that all at once because we don't know that. Yes. Hello? Sorry. Oh, hi, Sam. Yeah, self.next.next. So this is sort of like self.next.next because this came from self.next. Does that make some sense? Yeah, and then this asdref is magical. This next is actually an option of a box, which means, magical, but we can still understand it. An option of a box means like this is, maybe this node didn't have a next. Okay, that makes sense. And then the box means this is something that owns the node. But we don't want to own the node. The whole point of this is that we're not even modifying the list, right? This iterator should never own parts of the list. It just borrows parts of the list. And it lets you borrow different items in the list. So asdref is literally built for this purpose. It's a method on option. And its goal is to turn the thing inside the option, so the thing in the sum case, into a borrowed version of that thing. So box, this is a little, I think I was too hand wavy before. How does box work? Box is a type, and I think box is probably has some magic. What am I doing? Box probably has some compiler magic, but a lot of it could be written in Rust. So box is defined in Rust, and we got a bunch of these like sort of attribute-y macro things. Like this one is literally just like for documentation, I think. It says like this box has existed since version 1.0.0 and it's been stable since then, or something like that. Don't know what this means. This probably just like makes it more searchable. It frequently in Rust code, like in the documentation, that is. This doc is going to be like Rust has its own documentation generator, and then search unbox is probably some macro that like I don't even know. That's not really the point. The point is this is not all that relevant to how things actually work. How does box do the thing that we want it to do? Box is a pointer, right? But we're writing it. For now, I'm going to ignore everything in here because it's not that important. Okay, so one of the things you can do with box is you can make a new one. Okay, they've hidden it in a function, which is actually good because we don't care too much about that. But the most important thing you can do with a box is deref it, which is what happens whenever you do like some box dot something, you're accessing a field on the thing behind the box, or at least usually, right? So when I do like box, when I do like this node, this is an ampermute of a box of node. So actually what I do here with node.elem is I'm accessing the element on the node. Where is that node? That node is is this node. It's the one in here. So what's actually going on here is that the dot is dereferencing this bit and then somehow dereferencing the box, right? The node is behind the box. The box is a pointer to that node. How does that work? Well, in the language, there's this fancy trait called deref for dereference, that if you implement it and you implement the method deref that returns a reference to something, then you can use your type that implements deref like a pointer. And all the magic stuff happens. Like, you can do this, and it'll dereference it, right? It's built into the language that if node were a reference, we can do .elem, and it actually gets the element on the thing that's referenced. But it's not built into the language that it works with box. Box is just, at least mostly, written in Rust, and you can write your own. So what goes on there is first it turns it into a reference, and then it does the automatic stuff. The reason I'm talking about all this is because this next .asdref says, okay, the thing inside the option, turn it into, basically call deref on it. So call deref on the box. In this case, it's a box inside the option. So what we get out from this as deref, this is an option of a box of a node. What we get out of this as deref is an option of an amper of a node. And that's what we want. This is an option of a reference to a node, right? An amper of a node, I guess is what I said. The reason why this has to be a method and why it can't just be magic built into the compiler, I guess, is because there's the option in the way. You know, that the deref coercion works automatically. Like if this were just a box of a node, then I could use it like it was a reference, almost certainly. And the coercion would just sort of happen because it already implements the deref trait and the compiler uses the deref trait and automatically applies it. But because it's within this option, it would have to do a weird thing. It would have to turn this option of some type into an option of a different type. And the compiler doesn't do that automatically, partly because it's kind of hard for the compiler to do, and partly because it would be really confusing. You know, it would be maybe too magical. So this is sort of magical, but this is like, okay, compiler, turn the thing inside the option into the thing it dereferences into, or into a reference, not into a fancy thing. And the term, I think I said this before, the term for what box is, by virtue of implementing deref, is a smart pointer. And smart pointer is more of a, no, smart pointer is like a language agnostic term. So C++ has unique pointer and shared pointer and some other things. Because C++ has a similar way to make something that acts like a pointer, similar to this deref trait. So yeah, basically, implementing deref is how you become a smart pointer, and then sometimes you have to do shenanigans. That was a lot. Does anyone have any questions? That was sort of mostly tangent, but I'll make it more important in just a second, or more relevant in just a second. Please speak up, even if it's like a malformed question.
My mic wasn't on.
Yeah.
So a box is not a smart pointer by itself. We have to first implement dereference, is what you're saying?
Well, we didn't have to
Or
implement it.
I thought that
This
already
is,
came implement. Okay.
yeah. This is in the standard library. And this, literally,
Okay.
implementing deref is what makes box a smart pointer. We can make our own smart pointers by implementing deref.
Okay. That
Does
makes
that, yeah, okay. Thanks, yeah. So then we just return from this little lambda function here, we return a reference to the element, which means that in the end we return an option of a reference to an element, which is exactly what we're trying to return, because our self item is a reference to an element, and we return an option of a self item. Okay, so I spent a while on that, but the reason is sometimes when people are iterating over a list, they actually want to manipulate it. Sorry, it's someone, yeah. No. Yeah. Box is Rust's unique pointer. Georgie. This is happening in the text chat if anyone else is confused. Yeah, and there's what's going on, and maybe it was confusing, but what's going on here, there is this thing, unique, but that's a unique raw pointer in Rust. It can sometimes be useful, but it's really like in it you to use it you have to do unsafe. And we'll get more into that later. Shared pointer. Are you asking a question about shared pointer or? Yes, we will get to that. I think it's the last thing we do in this meeting. So just put a pin in that. Um, okay. So what do we want to do? We want IterMut, which is basically just iterator, or just iter, except um, it has a different name, and it lets people modify things. So instead of being an amper tick a node, it is, actually forget how this works. Does it work like that? It does not work like that. It works like that. Oh, but I also have to change the name, otherwise it complains about that. Okay, yeah. So far so good, right? Um, but it doesn't do anything yet. Okay, well let's make one. I guess that's the simplest thing to do before we even think about the logic. Um, okay, does anyone have any ideas as to what we have to change to give ourselves a way of making a, not into iter, sorry, IterMut. Not that. Let's say it's IterMut, and this returns IterMut. Does anyone have any ideas as to what else we have to change? I just changed the names. Dima, I think you're muted.
Doesn't it have to actually get ownership if it's going to edit it?
Okay. This is an important thing. It does have to do something different to, like, it does have to get, well, it has to get a mutable reference to it, but a mutable reference does not constitute ownership. The best way of thinking of it, I think, is that ownership means if I own something, whether I'm a type or a piece of code, it means that I'm responsible for freeing it. Um, it's a little bit more complicated than that, because if you own something and you're a piece of code, you don't have to free it. You could give it to someone else and then they free it. But ownership is saying, you know, with this piece of data is the ability to free it. So when I hand this to someone else, they get to free it. Or if I don't hand this to anyone else, I free it, right? AmperMute doesn't have that property. AmperMute says I reference it, and AmperMute says I am the only person who references it, and it says I can modify it. But the one thing I can't do is free it. I'm still just borrowing it mutably. I'm able to look and touch, but not destroy. So we need to do something differently. The problem is this as deref, even though it doesn't seem, it's not like as immutable deref, but it is explicitly it's a method on option that explicitly returns an option of a reference to the target, not a mutable reference. So this is common. I think I've mentioned it before, but there's sort of a convention where if you have like an as ref or an as deref sort of method, there's going to be another method named exactly the same thing, but with mute at the end. And this is exactly that. A couple of things changed in the signature, though. One, now we're getting an option of an amper mute of the target, which is nice. So we're getting the right thing. But also, as deref mute takes a mutable reference to self, which makes sense. In order to turn our option, or in order to get a option of a mutable reference of the thing inside of our option, we need to be able to modify the option. Like it's sort of a like I need privilege. It's like a good metaphor is if I am a user on a computer and I try to delete a file, or no, if I'm a user on a computer and I want to give you the ability to delete a file, I should be like the only way this works, the only way this makes sense is if I myself could delete that file. I can't give you permissions I don't have. The metaphor here is, as deref mute can't give us permissions it didn't have. It's giving us the ability to modify the target, so it has to be able to modify the target. And this has it's more than just that. Like borrowing something mutably means that there can be only one such thing, borrowing it mutably at a given time. So because of this return type, actually, I'm not entirely sure which part of the function does this, but altogether, because of all this, this means that when someone calls as deref mute on an option, no one else can modify that option except through the return of as deref mute. So this return type has to be, this thing that we returned has to be dropped before we can start modifying the original option. So that's kind of tricky. But yeah, is there anything else we have to change here? I think there's just one more thing we have to change here. And I sort of hinted at it with my whole rant there. Also, Dima, I don't know if you got to say any of the things you were saying, though, when you were muted. Sorry. You're good? Okay.
Would we have to change the return type?
I already did.
Oh, yeah.
Um, but yes. So just to make it more of a hint, two things changed between asDref and asDref mute: the return type and the thing it took. For us, we have just changed the return type and the thing it does. Is there something else we need to change?
The parameter itself, the self parameter of itself,
Yes. Yeah.
the
So what should I change it to?
amper mute.
Yes.
What is it?
And what
Okay.
does this, let me just save it without that, and then it says, cannot borrow self.head as mutable as it is behind an ampered reference. So I'm trying to borrow it as mutable because this dot tries to borrow it as mutable because asDref mute takes it as mutable. And I can't do that unless I can mutate it. So it's exactly the same logic as before, right? So semantically at a higher level, you can't create an iterator that would let someone change this list unless you have a mutable reference to the list, unless you can change the list. Does that make sense? Yeah. And specifically what this iterator does, it doesn't do anything fancy. It doesn't let you like insert things into the list, but it does let you change elements in the list because someone can take this return from next and like dereference this in their code and then modify the element in place, which might be very powerful because they can do that with a minimum of copies. They can directly modify the element in the list. So that's cool. If they wanted to increment every number in your list, or run a method on every large struct in your list, this is much more efficient than copying all the structs out into a different list just to make them. It could be. Okay, so far, that's good. Now let's just try copying this code. and modifying it for IterMut. So I'm just going to try to replace all the IterMutes. This is obviously, I got it wrong again. Amper to kmute. Interestingly, next was already taking ampermute self because this is saying we can modify the iterator, right? This has nothing to do with whether we can modify the list. So in order to advance an iterator, we always have to change the iterator so it points to a different element. Okay. Here we have to do as deref mute. And then down here, is there anything we have to do to make this all work as a mutable iterator? I think you're muted, Dima. If you're sorry, someone else can.
Would
Yeah,
just adding the amper mute suffice to all of that?
like this.
Yeah.
Yeah, I think this seems right, right? So all we had to do is say like deal with mutable references instead of dealing with just normal references, right?
Why wouldn't the
Yeah,
like
go ahead.
value need to be mutable? Yeah, why would the value need to be mutable if we're just giving that? We're not actually giving the node or anything.
Because
I
in
think
the
that's
end
the
we
really
want
bad
to
part.
return a mutable reference to the value.
Oh, okay.
Like that's the real only difference between iter mute and normal iter is that we're returning a mutable reference to the
Yeah,
value in iter mute. Okay, so this
that
seems
makes
right.
sense.
And unfortunately it isn't. And it's wacky. And this is where I get to more fully explain something that I've been sort of glossing over, which is what it means to copy things in Rust. But first, let's look at this. Self.next. Cannot move out of self.next, which is behind a mutable reference. Consider calling asref or asmute to borrow the type's contents. Okay. So self.next is behind a mutable reference. So this is exactly the difference that I was talking about between ownership and mutable references. We can modify self.next all we want, but we can't move out of it because the contract that I have by having an amper mute is that I can do everything except for destroy this. I have to keep it valid all the time. The reason why I have to keep it valid all the time, this was our problem in our original linked list. Um, the reason I have to keep it valid all the time is because anything in Rust could panic. And when something panics, it unwinds the stack. It's like throwing an exception. It's basically exactly like throwing an exception. Unwinding the stack means someone else could it unwinds the stack and someone else could catch that, and they need to observe only valid states of the program. So I can't even for a moment cause self.next to point to like cause the thing that self.next points to be invalid because I might panic at any moment and then someone might catch that, like catch my exception basically, and then see um, the thing behind self.next in an invalid state. And that the whole rule with Rust is that safe, like things have to be safe by default. If they saw self.next in an invalid state, that would be bad. Um, okay, so I can't move out of self.next, which is behind a mutable reference. Let's ignore this help for now. I think it's actually not helpful also, but because the compiler isn't really smart, it's just guessing. Also, the way it is right now, I can't see when text chat shows up all that reliably, but I'll try to. Okay. The real question is, what the fuck, right? Why did this work before? Because before, in this code, like the thing at issue was that we only have a mutable reference to self. We don't own self, right? Owning self would be if this was like this, but then this would be a stupid method because you could only call it once, and that doesn't fulfill the iterator contract. You have to be able to call next on the same iterator multiple times. Okay, so how did this work? So the point is we can't move out of self.next. We always have to leave it valid. And we're trying to move out of it. Why are we trying to move out of it? Let me see. Oh, because we call map. Okay, right. Because map is going to take self.next and then turn it into something else. And I've talked about how Rust by default has move semantics, which means that by default that invalidates self.next. We can't use it again. Which means, our iterator is broken because it has this field that we can't use again. The reason why this is different than before is because this was an immutable reference and this is a mutable reference. You can just copy an immutable reference in the sense of, like I've talked about how Rust has move semantics before, and I've said that integers can just be copied, right? Like I can have an integer variable x and then pass it to a function, and I can still use x. But not everything can just be copied. Like our lists can't just be copied. So this thing can just be copied, but this thing can't because it's a mutable reference. Let's think about why. Well, semantically, why is that one of the rules with a mutable reference is that only one can exist to any given thing at a given time. So I can't just copy this and leave the old one alone, because now I have two mutable references, right? This map will eventually end up returning an option of a mutable reference. So now I have two mutable references, at least briefly. I have one, or actually until this line runs, right? This line changes which mutable reference I have in the iterator, but until this line runs, here I have two mutable references. I have the one in node, and I have the one in self.next. How does this work? There is a trait in Rust that is very fancy called the copy trait. I don't know how to get to that best. Let's see. No. Rust up doc open. No. Rust up doc dash dash std. Then if I search for copy, we see the copy trait is a trait for types whose values can be duplicated simply by copying bits. So definitely integers can be copied just by copying bits. Immutable references can as well, right? Pointers, you might think, can, right? Pointers are just, I know where something is. I can tell you where something is, and that's fine. The key thing is that mutable references can't. Mutable references can't, because then we end up with two mutable references to the same thing, which is bad because now two people can be modifying the same thing at the same time. But there's this other thing, clone. This is a syntax for basically inheritance in Rust. What this says is that in order to implement copy, you have to implement clone. Clone is another trait, and it has one required method, and this you can implement if you want to optimize something, but let's not worry about that initially. Cloning a type is basically copying it semantically. What that means is different for different types, but who is familiar with the notion of like a deep copy versus a shallow copy in programming? Okay, yeah. So traditionally, clone is a deep copy. Sometimes it's a shallow copy, but traditionally it's a deep copy. And what that, like, just as a refresher, what that means is, like, if I implemented clone for a vector, that would mean that at the end of the clone, I would have two separate vectors. Everything would be deeply copied. And then if I modified one, it didn't modify the other, right? So the reason why clone and copy are different is to make it clearer that only certain things can be copied just by duplicating bits. A vector can't just be copied by duplicating bits. A vector, you need to allocate room for the new thing and then move everything over. Like, what I mean is that a vector can't be copied shallowly. Copy here is like the most shallow copy possible. Copy means we can duplicate it simply by copying like the bits directly in the struct. So we can't do that with a vector or anything that contains a pointer, really. Anything that contains an owning pointer, because just copying the bits would just copy the pointer, and then we'd have two pointers to the same thing. And if this were a vector, right, if we had two vectors with the same pointer to the same region of memory, we have a giant problem. We're going to free one of the vectors, we're going to drop it, and its destructor is going to free its pointer, and then we're going to drop the next vector, and it's going to free the same pointer. That's a double free. That's undefined behavior, right? So things with owning pointers, things with boxes, can't be copy, but we could decide what it means to clone them. We could say, you can clone a vector even though it has a box inside it, or you can clone our list even though it has boxes inside it. So why are these different? It's because in C++, we just have the copy constructor, which sort of serves this purpose, right? I guess implicitly, we have a copy constructor that works by just copying the bits. But you can define it to do whatever you want, like with clone. The reason Rust does this is because this way, cloning is explicit. Cloning never happens automatically. You always have to call this method. Whereas copying happens automatically. But it does mean that there's a lot of magic, because in this case, what we were taking advantage of was that an immutable reference implements copy. So what's happening here is that this map call duplicates self.next, and now node has a copy of the thing inside, or it duplicates the thing inside self.next. It duplicates this. Now node has a copy of the thing inside self.next. And that's fine, because with immutable references, shared references, that's fine to do. It's not fine to do with mutable references. Okay, so the solution, first of all, does anyone have a question about that? That was a bit of a mess. I can try to write out an example, or, yeah. I can try to write out a brief example. I think I'll do that, actually, but...
I think I got it, but
Okay,
just
yeah.
one question. Why is clone required for implementation for copy if, like, clone is
Right.
the deep copy and copy is the not deep one, the shallow copy?
Right, good point. So, that's a really good question. So the way to really think of it is that clone means this thing can be copied, or this thing can be duplicated in some way. Copy means that in order to do that, all we have to do is a shallow copy. So it's not so much that clone is the deep copy, it's that clone is copying in general, and then copy is just duplicating the bits. The names get complicated. I think Faultlore herself has an interesting. She wrote this book, right? She has an interesting thing on deinitializing, destroy all values, deinitializing, designing or was it here, or did she say bit copy here? Yeah. It's not important what all she's talking about here, but this is also good reading. Like, this is kind of language agnostic. Understanding Rust definitely helps, but this is like, what does ownership really mean? I'll put this link somewhere if I remember to. She says the one exception is that she's going to use bit copy for the kind of shallow copy Rust calls copy, because the word copy is way too overloaded a term in programming for me to just throw around, right? This is the issue. Copy and clone, like, the difference is that copy is a kind of clone, where all we have to do is copy the bits. So the reason why we have to implement clone to implement copy is because copy is just saying, yeah, you can copy me, and it's really simple. Clone is saying it is possible to copy me by doing something. Maybe you have to allocate more memory. Copy is saying you can copy me, and all you have to do is copy my bytes, copy my bits, right? So what that means is, like, integers implement copy. They also implement clone. I could write code that's very, very silly, like I could do something like, where is it? Let x equal 5. Okay, what's going on here? We don't. Oh, duh. Let x equal 5, and then, like, what's something that I'll just, yeah, up when r takes an integer and then prints it for whatever reason. The point is, like, this is what you can do with integers or anything that implements copy, but you can't do it with stuff that doesn't implement copy. I could do this. I'm just being more explicit. I'm just saying, hey, I can, please clone this x before I give it to bar. But what's interesting here is, what if x were like something more complicated? What if it were a vec? I don't think I've talked too much about vecs, but they're just vectors, right? So I can do, there's a funny syntax for initializing them. It's a macro, but I can do like 1, 2, 3. So now it's a vector of these things. And now this takes a vec of I32, but it still just prints it. I think you can just print a vec. No, you can't. You can debug print a vec. So this is like, there's no, the reason I had to do that is there's no defined way to print a vector and make it look pretty. But if I just want to do a debug print, which is what I do with this syntax, then there is a default way to do that. It'll put like square brackets around it or something. I don't know. So I can definitely do this because I'm not actually reusing x, but I can't do this. What happens here is that I call bar, and it says value moved here, and it says down here, like, use of moved value x. So because copying vec is expensive, because it involves running arbitrary code, not just copying the bits, we have to be explicit. But copying integers, we don't have to be explicit. All we have to do is, no, what do you do? All we have to do is this, and that's just to save us some typing, and because copying just the bits of something is not very expensive. So Rust doesn't think we should be worried about the performance implications of that, or the semantic implications of that. So that's, I guess, my brief example. Okay, how do we fix this, right? It should be possible. We fix this in the same way that we fixed it sometimes when we were dealing with options of boxes. Because you can't, here, when I'm pushing, the reason why I did this is because if I didn't do .take, then I have a problem. I'm moving out of self.head, which is behind a mutable reference. Because I can't deinitialize self.head. Here's self.head as a box, right? So I do this .take. What .take does is it removes our head and replaces it with nothing. Okay. What we want to do here is actually exactly the same. We want to take what's in our next, replacing it with nothing. Next is, again, an option of something. It's just an option of a mutable reference, not a box. But then we'll fix that right down here when we assign into it again with the new next. And that fixes it entirely. We were just getting away without the .take because it was safe to duplicate this reference. But it's not safe to duplicate this one because this one's mutable. That was a lot, and I think I will revisit that next time. I will try to think of a way to revisit that next time as well, but and I guess at this time especially, like I didn't really read from this, but I definitely went through all of it, so I think it'll feel less redundant to read this. That's kind of cool. But yeah, so she writes it. She does exactly the same steps as I did, and then she's very impressed. And it's kind of funny because she's of two minds here. She says IterMut is wild, but then it seems like, which in itself it seems like a wild thing to say. Surely it's identical to iter, right? Like, why? So there are two things to understand. One, why is it awesome? And two, why is it so normal seeming? Well, it seems very normal because it's just the same as iter, right? Except we want to let people modify it. Let people modify the item. What's awesome about it is that we have just implemented a piece of code that takes a singly linked list and returns a mutable reference to every single element in the list at most once. And it's statically verified to do that. So, yeah. It is a rule in Rust that we can't create two mutable references to a thing. So if it were possible to use this IterMut to then get two mutable references to the same item in the list, that would be a problem. But it's not possible, right? Because I get the mutable reference, and then the next time I call .next, I get a different mutable reference because this code runs again. So we know that, right? Like, that's a human thing. We can reason about it. This implementation of iterator never gives us the same item twice, right? That makes sense. But what's amazing is that the compiler understands it. The compiler understands that because I never do something funny with this ampermut, because I'm just passing it around and I'm invalidating the old one each time, that's why I did take, then things only flow in the direction of or what always happens is there's an element in the list, and then at some point we have a mutable reference to it, and that's fine. And then at some later point we return a mutable reference to it. And we do that at most once because we grab it out of our mutable reference and we give it away, and we replace our mutable reference with something else, right? Actually, the compiler doesn't need us to do this, but we need to do it for correctness. Otherwise, our iterator just returns the first thing and then blows up the next time because we left none in there. Because take puts none into the thing we're taking from. So, yeah. This is pretty impressive. Like, another important thing, like you might think, oh, iterators, obviously they only return references to each item at most once. But no, you might have an iterator that loops over the items, right? You might have an iterator that never becomes exhausted. I keep asking for the next item, and it keeps giving me either the next item, or if there's no next item, it loops back to the beginning. So we could have written that. But if we'd written that, Rust would have had to say, your code is invalid, because then you created two mutable references to the same thing, or you might. But Rust knows that it doesn't work like that. So this is just kind of impressive. What's interesting here? No, I'm gonna leave you with one last thing, but then I'm gonna go back to this next time. I just want to say that most of what we'll be doing is going to be moving on to the next list, and this next list is takes advantage of the Rust alternative to what is it? To shared pointer, Georgie. It's called RC, stands for reference counted. And what this is they call it a persistent singly linked stack. There's sort of a problem here. There are like 9,000 different terms for what persistent means in this case. What this means is this is a list that is fundamentally immutable, but we can still do useful things to it. So this is a list that you might be familiar with from 341 if you took 341 and did some F sharp or some Haskell. Lists in those languages, you can't modify them, but you can still do useful things because you can prepend onto them very cheaply. You can cause new lists to point to the old list. And you can also remove items from them very cheaply. You might think, wait, removing? That sounds like modification. Well, all you're doing, you're not changing the original thing. You're just saying, I'm looking at the same list, but I'm starting from the second item. Like, that's my new list. My new list is the same list as before, but only from the second item on. And with this, we can have the underlying items, the underlying things inside, never change. But we can share ownership of all those things inside, and we can still do useful things like add to the beginning. At a high level, how this works is that now we need a pointer where the thing it points to stays alive for as long as there's any pointer to it. And the reference counted pointer does this by keeping a count of how many things point to the node and keeping the node allocated until 0 things point to it. But I think next time, before I really get on with that, I will go back here and clear up something. If you have any questions, or if you can develop any questions, please do so before next time. And I will, what is it? I'll try to answer them, and I'll talk a little bit about some of the ways in which this is very impressive as well. I'll actually detour a bit to talk about vectors, because I think they can be a simpler way of explaining something. But anyway, thank you. Does anyone have any questions right now? Okay. Whack.